Huge bummer. All of your police cars are broken, but on this nearby highway, you need to figure out how fast the cars are traveling, because you still need to, hold up the law, I suppose. But all you have, you're all the way over here, and all you have is an open reel measuring tape. I'll attempt drawing like this thing, and it has measuring tape. And you have a compass, so from north. And then you have your brain. Look at this brain. Yeah. And then you also have squigglies. And then you also have the law of sine and cosine. Turns out with these things, you can figure out how fast the cars are traveling on the road without even being on the road or without some sort of device like a speed gun. To start, we used that open reel measuring tape, took it to the center of the CMC campus, and then measured 100 feet in each direction. And this gave us our baseline 1 point and our baseline 2 point. We needed 3 points on the road, and we chose a purple sign, a speed limit sign, and a stoplight. Now, the thing about these points is that they're all on the same side of the road, which is important to try and make your line as straight as possible. To start, we wanted the baseline 1 and baseline 2 angles, and what I mean by that is we took the compass and then saw where the baseline 1 and baseline 2 fell on 360 degrees. And then from there, we had to measure every angle to every point from each baseline point. Now, I know that sounds confusing, and the data is even more confusing, but hang in there. And the process of this was one person would hold the compass up to like a metal rod to get a good sight on the point, and while a second person would look at the phone and record the angle. We wanted an average, so we took 4 measurements each. This means 16 angles for every single point. And here's the list of data, and I know this is incredibly confusing, so here's a more comprehensible list of averages. So where are we at this point? Apparently we're at a little kitten, but that's just a distract. Come on. Okay, and we have a little baseline here. So we'll call this CMC, and this is baseline 1, and this is baseline 2. So we have our points on the road. This one happened to be very close to like the baseline angle, which I think was a mistake, and you'll probably see why later. So we have these 3 points. Here is point 3, point 2, and point 1. So this is the road back here. I'll just call this here. We'll do a little road thing. Road. And the cars are traveling in between these points. Do my best to keep these lines somewhat straight. And we found every angle from the baseline points from the base. Wait, what am I trying to say? Here is the angles from the baseline points to the points on the road. That's what I'm trying to say. And this last one. And then this one. This one. This one. So this is a rough idea of what we have a bunch of triangles everywhere, and this came from all the angles that we took. We got our average angles, which I'll show here now. If we take an arrow extending this angle here and this angle here, we have 34 degrees. Does not look like a 3, but bear with me. 27 degrees. And then these are all the averages, by the way. This is the average angles. 62. This one came out here. 71. And then this one was like 114. And this one, 118 degrees. So we have all these angles here, but these aren't the angles we're going to use for the law of sine and cosine. What we want are the angles inside the triangles. And, well, how are we supposed to find those? Oh, and by the way, hang on. This is 123 degrees. So I had to redraw it because I messed up, but that's okay. And I forgot to mention that this angle here is 115, and this angle here is 295. Now, if you're still confused about, if you're still confused about how I got these angles, I want you to imagine a compass here that just points north. So if you were to spin this compass, or if you were to hold this compass and spin around, you would have spun 360 degrees. So when we had this compass, it was just giving us the degrees where that landed. So for example, see how this one is 118 degrees right here. If we were to stay on baseline 2, point it towards this point, we would have seen 118 degrees on the iPhone, and that would have looked like this, for example. So I hope that makes sense in how we got all of these angles here. They're still not the angles we want, because we want the angles inside here. For example, if we want to find this angle, we'll just add this angle to this angle to that angle, and that is like 1 degree plus 43 degrees plus 37 degrees, and that all comes out to 81 degrees. So this angle would have been 81 degrees, that necessary angle. With a similar process, here is every single necessary angle that we need. Now that we have all those angles, we can start finding some distances here. So our goal is to find the distance between the two farthest points on the road, and I just wanted to call that capital D. Now we're going to use the law of cosine in order to find that. But with the law of cosine, we're going to need this side, and the angle in between them. And in order to find this side and this side, we're going to use the law of sines first. So in order to do that, we're going to have this angle here, which I know is 8 degrees. Because it's opposite our baseline length, and then this angle here to find, we'll call that L, because we need this distance here. So the law of sine is sine, or we'll put the distance on top, the length, we'll go A over sine A equals B over sine B equals C over sine C. And this is everything in a triangle. So these are the three sides, and A, capital B, and capital C are the three angles opposite to those sides. If I just a quick example of this, if I have here's capital A, little triangle, and the opposite side to that, capital A, is little a here, and that's this representation of that. So in our case, we're going to have 200 feet, our baseline, 200.00 feet, over sine of 8 degrees equals L over sine of, and I have to find this angle really quick. There it is, sine of 81 degrees. So now we're going to solve for L. L equals 200.00 feet over sine of 8 times sine of 8 degrees, 81 degrees. And when I do those calculations, I get L equals 1,419.37 feet. Okay, cool. We have L, but now we need L2 as well. And L2 is going to be an identical process, but with some different angles. And we'll say that L2 over the sine of this tiny little angle right there, which I know is just 1 degree, so sine of 1 degree equals 200.00 feet, our baseline, over sine of, 4 degrees. Do that calculation, and poof, L2 equals 200.00 feet over sine of 4 degrees times sine of 1 degree. We get L2 equals, what is it? Oh yeah, 50.038. We'll just call it 04 feet. Now remember, we're using these lengths here in order to find the distance with the law of cosine, but we still need this angle in between the lengths. Well, if you go back to the summary of angles, you would just add up this angle to this angle and get, well, I've already done it, theta equals 91 degrees. And when we look at the law of cosine, it says that d squared equals L squared plus L2 squared minus 2 times L times L2 times the cosine of the angle between them, which is 91 degrees. And when we plug in a bunch of numbers, we'll be able to solve for d here. So I'm going to start it down here because it's a long one. D squared equals 1,419.37 feet squared plus 50.04 feet squared minus 2 times 1,419.37 feet times 50.04 feet times the cosine of the angle between them, which is 91 degrees. We do all of that, and I've already done it, so lucky me. D squared equals, we have 19,594.32 feet squared. Now this is a ginormous number, and we can take the square root because this is feet squared and we want feet. So then we get d equals 1,421.12 feet. Now we needed to calculate how long it took the cars to travel in between P3 and P1, which was that total distance. That would give us a velocity, because velocity equals displacement over time. And we have displacement, but we don't have time. So here is the list of data we took for finding that average time, and our average time equals 15.12 seconds. Now we can find that velocity. V equals 1,421.12 feet over 15.12 seconds. And we get V equals 93.99 feet per second. However, our speed limit is in miles per hour, and right now we have feet per second, so we're going to use the factor label method in order to convert that to miles per hour. So we have 93.99 feet over seconds times 5,000, goes on the bottom, 5,280 feet in a mile, 1 mile, times 3,600 seconds in 1 hour. We cancel what can cancel? Seconds with seconds, feet with feet, and we're left with a velocity of 64.08 miles per hour. But our compass only gave us 2 significant figures, so we have to make this 2 sig figs as well, and that gives us a velocity of 64 miles per hour. And this might be a little disheartening when you learn that our speed limit was actually 50 miles per hour, so we're obviously over by quite a bit. And now we can start talking about why that number is so off. So what went wrong? Well, a few things. The compass we used was incredibly inconsistent, and that's why we had a very high standard deviation on most of the angles. Like 10 degrees variance is way too high to get any good numbers for something like this. So we probably have some bad angles in here. Also, when it comes to large distances like we were calculating, the greater the length, the greater the error is magnified the farther you go out when it comes to angles. Second, I want you to notice how small of an angle it is from BL1, baseline 1, to point 1 on the road. This tiny little measurement wasn't accurately measured on the iPhone, which led to some impossible geometrical complications, such as, I don't know if you noticed, the fact that the angle of baseline 2 is larger than the angle from baseline 2 to P1, which is 118 degrees. Now, everything to the left of baseline 2 should be smaller than it on the compass, but when we did it, we found a larger angle from baseline 2 to P1. So obviously there's some complications with the compass. And third, human error was also a factor, kind of obviously. When all you have is a sight line and your hands to hold up the phone and point it towards the points on the road, there's going to be some human error involved with that. But how would you fix these things? Obviously, the biggest thing is a better compass. If we had a better compass with much more consistency, then I think our numbers would have been a lot better. Also, if we had used an electronic measuring wheel, this would have helped us get a much better baseline length and hopefully in a straighter line. In conclusion then, by obtaining the speeds of the cars with minimal supplies and a lot of math, we arrived at a result that wasn't too disappointing but definitely off. And while our methods could have easily been improved to deliver much more reliable answers, I think we did a pretty decent job of obtaining a speed that is at least in the ballpark of what we are hoping for.